It's a pleasure to introduce Scott Smithers, who many in the room will know. Scott's a geomorphologist, started his career at Wollongong and moved to JCU 20 years ago, I noticed.
I was 12.
And it's been a great pleasure to hear what Scott's got to tell us today. He's an expert in geomorphology, particularly on the GBR. I wrote one of the key textbooks on it. I've been in the field with Scott in Chagos, and his tools of choice are Dunlop volleys and a handsaw from Bunnings. Nothing else but a speedo. So.
I knew you were going to say that.
Apologies.
Thanks. Okay, thanks everyone for coming. Look, today I really just want to, talk a little bit about geomorphology, and I guess some of what I'm going to say might be familiar to some of you, and some of it maybe won't be. But I guess just to start with, a little bit of context, and I guess back in 2012, a little bit before that in fact, when the ICRS was going to be in Cairns, or it was in Cairns, and the planning around it, there was no plenary that was an earth science plenary, and didn't worry me, although I was surprised. But it was interesting that on CoralCoE there was a bit of a heated debate, and I read some of the stuff there, and it sort of concerned me because it almost came across as if there was this sort of adversarial relationship between reef ecologists and some of the people in the more earth science end of the spectrum. And, you know, I'm not a geologist, I'm a geomorphologist, and I want to make that clear. But the questions that were being asked about earth science and its relevance to some of the big problems that the reef is facing, I thought were pretty relevant. And one of the posts on CoralCoE had this statement, and it said, "In reviewing the topics that the plenary speakers are to address at the next ICRS, I have to ask how important are any geological questions compared to those listed below?" And there were a whole lot of ecological and management type questions that were there. So I actually think that rather than take offence, that was probably a fair question. And, you know, it's up to people in the earth sciences really to try and justify why what they've got to say is interesting, and maybe we haven't done a good enough job of that. So today really what I want to do is just give you a bit of a cook's tour, in fact, just a couple of snapshots of some of the work that I've been doing over the past couple of years, which is sort of relevant to what, if you read the Outlook report, are some of the key questions that are facing at least the GBR. Now, you know, this isn't going to go anywhere profound, but hopefully at the end of it today, I'll convince you that some of the stuff that people like I do is actually relevant to some of the ecological questions and the management objectives that many people in the room are dealing with on a day-to-day basis. So first of all, I want to talk a little bit about inshore reef growth. I think most of us would be aware that, you know, they're under a whole lot of terrestrial pressures and are in ecological decline. And I want to touch on some of the lessons from the past, what we know about the growth histories from these reefs, and some of the observations about what we do know and don't know. I also want to talk a little bit about geomorphological change and conservation planning. I think a lot of the management of the GBR is rightly focused on some of the key ecological concerns and parts of the system, but I guess I really would like to just fly the flag for geomorphology as being a relevant framework to also consider in some of those deliberations. And I'd say actually it's probably more than relevant, it's really important. And finally, I guess another thing I'm involved with is the geomorphology of Rain Island, and it's a critical turtle nesting habitat. And I'm going to talk a little bit about that today as an example of where geomorphology matters at a more immediate time frame. So there's Rain Island. All right, I guess at the end of today, really what I'm hoping is that you sort of feel a bit like I do, and really what I'm about is trying to get people to understand that there is value in geomorphic and sedimentary records of reef and landform development. They provide a context for understanding ecological and environmental change. Now, you know, sometimes that isn't statistically as robust as you might hope if you're an ecologist, but, you know, we have to deal with different sorts of records and different sorts of data, and that's just the nature of the beast. I would also say that the converse is also true. You know, the geomorphology and its development over time also influences the ecosystem. So there are these feedbacks both ways, and that's something that I also want to stress. I guess really what I'm all about is trying to demonstrate that geomorphology and geomorphic data has relevance to ecological and environmental research. And that's what really motivates me. All right, so to begin with some of the stuff, to begin with the Inshore Reef work, I guess I've been working on the Inshore Reefs for about a decade now. And I guess we'd all know if we read the Outlook report or just read the newspaper that the inshore reefs of the GBR, particularly in the central and southern GBR, are exposed to poor water quality, and this is having a major impact on the quality of the systems. Those systems are naturally turbid. The water in that part of the GBR and to the north as well is turbid. It's not nice and clear, but as well as there being sediment in the water now, we've got elevated sediment, we've got different types of sediment, we've got nutrients and herbicides and pesticide loads, which are above, obviously, pre-anthropogenic levels. This statement here is actually out of the 2013 scientific consensus, and it basically attributes poor water quality associated with terrestrial runoff to as a major threat to the GBR and one of the major drivers of the ecosystem decline that's been witnessed over the past few decades. Not just to the reefs, but all the interreefal areas and habitats such as seagrass, etc., etc. So, one of the motivations for me to look at these inshore reefs is obviously they're exposed. Effectively, they're the front line, if you like, of some of these pressures. And understanding how they've grown in the past, both in terms of how they've come together geomorphologically, what the tempo of that growth has been, what the species assemblages are that have contributed to that growth and how they've changed through time. And also, the records that are contained within the reefs to do with the sedimentary system is really what some of this research has been mainly focused on. So, over the past decade, we've looked at the geomorphological development. I should say this is not just me, this is particularly work I've been doing with Chris Perry, but a whole bunch of other students and collaborators, Steve Lewis as well at the front. We've looked at the geomorphological development. So when I talk about that, I mean what are the controls, where do these reefs occur, why do they occur, where they occur, how fast do they grow, the rates at which they grow, the sort of way in which they come together. Of course, the reefs themselves are constructed by the coral communities that live there, so in the internal fabric of the reef, they preserve a paleoecological record. You can actually take a core and see what the species assemblages are, and if you get enough cores, you can say something that's marginally robust about what sorts of corals have been there, how they've changed over time, and maybe even link them to environmental drivers. And that relates to the third thing there, the environmental histories. Now, we've got a record that we've collected from about 11 different inshore reefs. Some of them are named here. There's other ones to the north up near Princess Charlotte Bay, and there's also some other reefs that Emma Ryan, one of my students, is looking at down off Bowen. But there's also a fair bit of work being done prior to our investigations, and we've included some of the data from those records in some of our analyses. But for just the stuff that we've collected over the past decade, we've got about 100 cores, which is a pretty impressive record. We've got about 400 radiometric dates, so we've got reasonable chronologies for our records. And we've done a lot of mapping and a lot of video transect work, a lot of ecological surveys over the reef flats and shallow subtidal. And we've got pretty good terrain models for a lot of these reefs as well. So, we've got a pretty good record for these reefs, which many of you wouldn't even know were there if you go there on the average day, knee deep of water over them, and you can't see them there. The hidden shallows is what we have called them on one of our research grants. For some reason, so there's supposed to be a whole lot of pictures that are not coming up here. So basically along the bottom here, working on Macintosh, there's a bunch of different types of these reefs that I was hoping that you would see. So there are basically mainland attached shoal reefs, there are fringing reefs, there are actually short attached reefs, and there are turbid zone reefs, which are basically the platform reefs or islands that are located within what we call the terrigenous sediment zone, which is usually shallower than the 10-metre isobath and back to the mainland coast. So this could be a problem if this is going to... Alright, so in looking at these reefs, this is what we were really trying to get a handle on. We're trying to know when and where they established, How long have they grown? Has that grown been continuous or has it been episodic or pulsed? And what is their current geomorphic state? And we tried to develop linked paleoecological and sedimentary records to get an understanding of how these reefs have changed over time. Typically what we do is we started off trying to use hydraulic drilling, but we found the easiest way to get the best cores is to simply do what's technically called percussion coring, but it just means getting a piece of pipe and hammering it into the reef. And that's what we do. And the advantage of that system is you collect all the sediment and the corals, and you can basically get a complete record. If you use hydraulic drilling, often you flush away a lot of the sediment. So it's a fairly low tech, but it actually works the best. We typically do transects from the high upper tidal right down to the shallow subtidal, as deep as we can go. And by doing this method, we generally collect the whole Holocene growth record. So we go down into the substrate on which the current reef is actually begun to grow on. So we get the whole package. Okay, so I'm not going to show you page after page after page of cores from all these different reefs. What I really want to do is just tell you some of the things that we found about these reefs, which I guess make me feel a bit optimistic about them. So this set of logs here, which has got a lot of information on it, don't worry too much about it. But the first thing I guess that I'd like to say is that these inshore reefs, they grow over a diversity of substrates, which is actually great because it means the potential for these reefs to grow is actually fairly large. So if you read the textbooks, what you'll typically find is most people argue that you're not going to get reef growth unless they're over fairly firm, consolidated substrates. But what we typically find for these inshore reefs is that they tend to grow over just about anything. Coffee rock, which is indurated sand dunes, Pleistocene clay, which is just like the stuff that's out here. So if you imagine sea level came and flooded the coastal plain, the stuff that would be flooded would be Pleistocene clay, and we find reefs that are growing directly over that. We find mangrove muds under some of the reefs. I don't know what's going on. There should be a picture of these different types of substrates. Lithic gravels and fine sands. The bottom line, as I say, is really that we find a diversity of substrates. The other thing I'd just really like to point out is that it's not unusual to record quite a few different species in these reefs. Many people go and they'll have a look at these systems at a low tide and they'll see turbinare, goniastria, the odd parietes and maybe a few Montipora. But if you actually do a detailed survey, which is actually difficult because visibility on these reefs is generally so poor, if you do a detailed survey, it's not unusual to find they're more diverse than you would recognise. 20 to 35 genera is sort of not out of the ballpark and quite common for most of the reefs that we've looked at. And that's both in terms of the contemporary community and also what you'll find through the core record. Okay, so this reef here that we have the cores from is actually King Reef, which is up near Curramine Beach, just north of Mission. It's a large mainland attached inshore reef. And basically, I'm getting a bit lost because of the missing diagrams. Basically what I was going to show you at King Reef was that, I forget, was that there was a bunch of different, not only a different, let's go back, sorry. What I was going to show you actually was the age on these reefs as well, sorry. So these numbers down the side here, they're radiocarbon ages. And what you'll notice is that at King Reef, a lot of the reefs started to grow in the early just after 6,000 years ago. And you'll notice that a lot of the reef actually got to the surface by about 4,000 years ago. Now this is something that I'll touch on again later on. And the other thing that I'd like to show you, and there should have been another diagram there, which is not going to be there, is that through the record there's a bunch of different what geologists would call facies. Okay? And all a facies is really a way to classify different sediments, both in terms of the actual terrigenous sediment, the sediment that comes off the land, and also the carbonate, the stuff that's produced by the reef. And typically we find variations on three main types of facies, and we can pretty much say that pretty much over all the growth history of most of these reefs, it's been high sediment loads and often quite muddy. And definitely what we can say is that during discrete periods, there are episodes where there are large lumps of fine mud settling over these reefs way back before European settlement. Now, I really want to say at the outset that I'm not here to say that we aren't doing bad things to the reef. So I do think that the reef is not as good as it was prior to Europeans getting to this part of the world. But I think this does provide some context for maybe how these types of systems can perhaps bounce back if we take a bit of the pressure off. So we can often find whole layers that might be 20 centimetres thick that are just fine clay. And they're often bracketed by age across more than one core, which suggests that it's a sort of, it's not just a little local effect, it's a more of a reef scale or perhaps even bigger scale. All right, now when we look at the whole suite of reefs, one of the things that you'll notice if I showed you the infinite number of cores that we've got, one of the things that you'll notice is that these sort of age patterns are quite common. So often the earliest reefal age is around 8,000, something like that. And at King Reef, we can see that the fossil microdale age is about 4,000. The key thing I really want to emphasise there is that, you can see that some of these reefs have come up from 3 or 4 metres depth, and they've done that in just over 1,000 years. So these reefs are actually, if you were going to use vertical accretion or reef growth as a measure of health, which you may not want to do, these reefs actually do rapidly vertically accrete. Now that's sort of good in one sense, but it's potentially bad in another, as I'll explain in a moment. So one of the things here, if we look at these numbers, which maybe you can't see, they're the vertical accretion rates, sort of 6 or 8 millimetres per year. Paluma Shoals actually is up around 10 millimetres per year, and some particular cores are even faster. That's remarkably rapid. Okay, lots of the outer GBR reefs are about half that. So, surprising result. Based on all the cores, we can come up with growth models, and for King Reef, this is basically what we think was happening at King Reef. So, if you were there about prior to 6,000 years ago, there would have been a coastline with some coffee rock. There would have been a dune on that at some stage. It's been blown away or washed away, and there were mangroves growing at the front of it. Basically, sea level rises, and we get a bit of turbidity and everything in there. But on some of this substrate, we've got enough permanence there for corals to get on and start to grow. And basically, as I said before, at a very narrow, really, temporal window, the reef gets to the surface. Of course, over that period of time, sea level is continuing to rise, so the shoreline steps back. Okay, so as the sea level rises, where the coast is moving inland. And so the reef is actually disconnected from the shoreline because it's grown up on that initial position, and then it infills over the back. And that's really what's happened at King Reef as an example. Okay, now one of the interesting things at King Reef is that despite popping up very quickly at that time, it really hasn't actually built out very much at all over the past 4,500 years, which is interesting. Why doesn't it do that? Now, at King Reef, it's one of our reefs. So if we look at what we find when we look across all the reefs that we look at, so this here is basically a sea level curve, 8,000 years ago to present, and this is sort of a window in which we think that reefs in turbid zones can possibly grow. They've got to be within the photic window. Okay, now all those different crosses are dates from reefs, and these circles, which you don't really need to know what the reefs actually are, it's the minimum initiation age. So it's the time at which the reefs that we've got the data from started to grow. I'll get this right sooner or later. And what we find is that they basically clump out into two clumps. There's the clump that clumps out around 6,000 or so years ago, and then we clumped another bunch out that are much younger than that, and there's a gap in the middle. So effectively, there are two populations of reefs. When reefs in the turbid zone started to grow, then they didn't grow for a while, and then another bunch started to grow. Now that's not to say that some didn't grow through that period, it's just that there wasn't any colonisation of reefs in this zone over that gap in the middle. And interestingly, when we look at the actual paleoecology of the species that are in the cores, it's pretty much the same stuff. Same sedimentary environment, same taxonomic assemblages. So, what's going on there is something that's very interesting. If we have a look at the southern GBR, and this is in our data, this is some data from the literature, although some of our colleagues working on the NERT program are coming up with a similar sort of hiatus in the middle. It seems to be a regional scale type phenomena. So the point here is that there's been a period of time when, for some reason, reefs didn't actually start growing and survive that well in the recent past, but well prior to European settlement. So just again, a couple of diagrams. This is Dunk Island, what's called a resort reef, so straight out in front of the resort. A lot of information there. The main thing just to be aware of is it's popped up about the same time roughly, grew to about the same time, 4,500, and then stopped. Nothing really happened there for a while. Now when we plot all these out a different way, and this is what we've got here, so we've got different parts of the reef and we've got the age structures, so this is time across the bottom. Okay, what you can see is that those two sort of groups become apparent again. So there's a whole bunch of these reefs that started up, grew pretty well and then effectively stopped. And then we've got another bunch of reefs which basically either started adjacent to the earlier but with a gap in the chronology, so there was nothing happening for a few thousand years and then they started again, or they've started up independently, there was nothing earlier. So really what I guess I'm trying to make you aware of here is that these are pretty simple systems in effect, but their growth histories and the dynamics of why they grow, where they grow, and how they grow, where they grow, when they grow, are actually a bit more complex than you might appreciate by just having a simple look at it. I think there's a lot of these reefs out there that we just simply don't know about. The other thing that we found when we've looked at a couple of these reefs, or a lot of these reefs, is that they do come together in different ways. So at Lugger Shoal, which is off Mission Beach, this isn't actually Lugger, this is actually Paluma Shoal, sorry, it's got the wrong label on the top. It's basically just a detrital accumulation of material. So it's a reef that's basically growing in situ, broken up every now and then, collapses down and traps sediment as it grows to the surface. This is actually, I've got those labels around the wrong way, sorry. This is Paluma, but it's not Paluma, it's Lugger. At Lugger, it's more of this model where you've got big, massive bommies that grow up to the surface and effectively form a structure that traps a lot of the finer material and the sediments around it. So there are different sorts of growth fabrics, is the thing I'm trying to get through. All right, now why do they grow where they grow? Well, that's a good question because, as I said earlier, most people will tell you that these reefs should be growing over hard substrate. And a lot of the work we've been doing over the last couple of years has been up in Halifax Bay. And we've done a lot of bathymetric survey off the Kirby. And so what you're looking at here is Tullakia beaches are down around here. And this is sort of, not very deep at all, 4 or 5 metres. And you'll notice these sedimentary structures. They're bed forms. They're just basically to do with the longshore currents going up and down that coast. And they've got about half a metre relief on them. And what we found actually when we started to map these and then try and map where the reefs were growing, the reefs are actually growing over those very subtle topographic highs which are controlled by the bed forms. So effectively what we've got in this situation is we've got coral reefs whose location is actually controlled by a sedimentary bed form, which is sort of antithetic to what you might expect. What do these reefs look like? Well, they're not obviously sort of like Maldivian reefs, but when you get them on a good day, they're pretty high coral cover, reasonable diversity. Often we'll find just massive stands of things like, turbinaria. But, there are patches that are, I went snorkeling out there, it's pretty nice. So, none of that's charted. So, I think there's a lot more of these sorts of reefs out there that we really don't know about, which is a good thing. Not that we don't know about it, but it's out there. Okay, I was asked to say at least one thing controversial, so this is it. Okay, so if you read a lot of the literature, and this is straight out of the Outlook report, these pictures get dragged out all the time, and they do tell a bit of a sorry tale. So we've got Savile Kent's photo down there off Bowen, Fort Denison, and someone else later on out there sitting on Goni Astria. And then Dave Wackenfeld came along in 1994, 20 years ago, and took this photo. And you can see it's a desolate sort of landscape. And 2012, somebody's gone out there again, I think it's Tara from UQ, and taken the same photo. And clearly there's been a change there. Now, what's this got to do with geomorphology? Well, as I said earlier, I do believe the reef has changed. But if you're going to use this sort of data, you need to understand what it is that you're actually looking at. And this actually, I think, is actually not correct. And without going into the details here, anyone who's done my third year subject will know that the reason though is that the inner part of the GBR has actually been bent up a little bit because when sea level rose, the weight of the water on the outer part of the GBR shelf, particularly in the central GBR, pushes the outer shelf down, which flexes the inner shelf up. And so the inner shelf reefs have actually got an emergent back reef platform. Okay, they grew up to sea level, but they've actually, there's been relative sea level fall because the land has gone up over the past few thousand years. So the reason why you don't see lots of live coral over these areas, and you can see that's a long way back from the tide on this day, is because it's emergent. It's not in the zone where we would expect to see live coral cover. The question is there reasonable coral cover in the part of the reef where we would expect to see live coral cover? And this is another photo from Savile Kent, taken near the same place. That's Gloucester Island. It's not Savile Kent, it's my photo. This was taken not that long ago, just maybe last year, I think. And whilst I'm not going to say that's a beautiful reef, it's definitely a lot better than the photo that was in the Outlook report. So the take-home message here is that you really need to be aware of some of the geomorphological history when you're comparing apples and oranges in this case, because I think, as I said, I'm not saying that the reef is in good condition, but I think it's in a better condition than some of those other photos would definitely suggest. All right, so in terms of the inshore reefs and how it might contribute to answering environmental ecological questions, I think the things I'd really like to stress to people who are interested in these reefs, which are interesting from an ecological point as well, is that you can go to very close proximity and see big differences in both the age of the reefs and their ecological stage. So something like King Reef, which basically did all its growing 6,000 years ago, and it was over with, versus Paluma Shoals, which basically started growing about 1,500 years ago and is still growing well today. They mature quickly, which means they get from start-up to the reef surface, to the sea surface very quickly, mainly because of the shallow water. They've declined and recovered in the past, which is good for us to know. I think what we're starting to see with all our broader mapping is that these inshore coral carpets, which might be incipient inshore reefs, are more widespread than previously thought, and we're starting to get a handle on where they might be, so we can start to predict where we might find them, which is going to be useful. I think further offshore where trawlers used to go, they probably destroyed them, but if you take some of that pressure off, then things might go well. And the last one there, not all dead reeflets are dead because of human impacts. Many are just old or emergent. As I say, I'm not saying that some of them aren't dead from from anthropogenic impacts. All right, I just now want to switch to geomorphological change, because I think it's something that I'm not sure that a lot of reef ecologists appreciate the pace at which it can happen. And I guess what I'm hoping that I can get through to people here is that it can actually happen quite rapidly, and people, I think, need to be aware of it if they're investigating broad-scale ecological questions. So this is a model that David Hopley came up with back in the late 80s, in fact, and effectively all it says is that reefs start growing on a substrate, and over time they grow to the surface. Eventually we get a reef rim at sea level, and that's when we call the reef mature. So once the reef reaches sea level, it's mature, and then when basically the rim becomes fully encloses the lagoon and then infills, basically we end up with effectively a sedimentary surface, and the reef is senile. So the controls on how fast you move through that depend on how far the reef has to grow up. So shallow substrates, you get to the sea surface quicker. What type it is. If it's more firm and so it's not falling over as often, then that will get you there faster. The size of the substrate. If this is a big reef, it takes a lot longer to fill the bucket up than if it's a small reef. And basically the relative sea level history that I just spoke about is also important. As I alluded to, the pace at which this can proceed is maybe surprising to some. Maybe I'm kidding myself. But of course, as the reef structure changes through time, it can transform habitats over time. And if those habitats are key and important habitats, or they're one moment they might be well connected and then they're not well connected to a whole bunch of other necessary habitats, then obviously that's something that I think managers and ecologists need to consider. And I would argue that perhaps those sorts of changes haven't necessarily been fully captured in the current zoning plan. All right, so what sorts of things am I talking about? So this is Pippon Reef, which is up near Cape Melville, okay? So a couple of years ago, we took some cores through there, and the main thing I really want to show you here is that, once again, this reef, which is about 2 k's in diameter, it basically, the oldest date we got was about 7,700 years old, but it filled up that whole lagoon in just over 1,500 years. So the reef grew up off the substrate, which would have been there when sea level flooded that part of the world. I'll talk about it in a minute. And then this has gone from being a subtidal reef structure to being effectively a reef that's had its whole lagoon infilled with sediment. And then we've got an island, a cay over here that's formed at the back of it, and all mangroves over the windward side. All natural and pretty quick. If we have a look at what the reef looked like during the Holocene transgression, so the ice caps melt, sea level comes up. If you were there 18,000 years ago, sea level was right out on the edge of the continental shelf. If you were there about 12,000 years ago, you can see that the northern part of the shelf, so Cape Melville's up here, all pretty much high and dry, even 12,000 years ago. 9,000 years ago, up around Cape Melville, still high and dry. Pippon Reef would have been a little limestone hill on the coastal plain, not a reef at all. And it's between 9,000 years ago and now that change has happened. Now, for a geologist, I'd say that's like that. For a geomorphologist, that's a reasonable amount of time. For an ecologist, you probably think that's forever. Maybe it is. But if we have a look at the time frames over which some of these reefs can change, this is a bit skew with because the size is playing an influence here, but the main one I'd just like to draw your attention to is the end one here. And if we look at some of our planar reefs, which are the ones like Pippon, what we can find is that, based on the average data set that we've got, they're generally small, which means that they can infill that bucket quickly. Basically, there's an average depth down to the substrate, based on the records which we've got, which aren't that many, of about 10 metres. So you drill down through the modern reef, you get down to the substrate on which the reef grew on about 10 metres below. And that reef is basically transformed from being a limestone hill on a floodplain 9,000 years ago to being, at some stage, a subtidal reef, a chrysenic reef, a lagoonal reef, and then an infilled reef over that sort of fairly short time frame. And not the whole 9,000 years, maybe 1,500 years. And I think that definitely is sort of an ecological time frame. If we have a look at when reefs on the GBR were doing their best stuff, this bunch of graphs here, these are the different sorts of reefs. Basically, if you have a look, you can see really the heyday for being a reef on the GBR was about 6,000 years ago. That's when most of the reefs were really powering away. So this here is when reefs got to sea level. And you'll notice a lot of reefs got to sea level around 6,000 years ago. This one over here is the growth rates. So basically metres per 1,000 years or millimetres per year. And you'll notice all the high bars, 6 millimetres, 4 millimetres, etc. They're all in that 5,000 to 6,000 years ago, long ago. And there's been a decline, once again, well before European Skycare. Now that decline is really to do with basically the natural geomorphological change. The reefs have actually done something which we call exhausting their accommodation space. They fill up the space in which they can grow into, which slows them down. If we have another look at this, so that's vertical. What about lateral? If you go to most reefs and you walk across them, go out to Maggie, you go off the bottom of the beach and it's dead reef and sand, and you walk out and the living reef's out on the edge. And across there you'll find microatolls, corals that look like truck tyres, and if you date them across, what you typically find, and they give you the age, the minimum age of the reef flat at that time that the coral lived. And what you find is a lot of the reefs, so these ones here, they basically put in most of their lateral extent in that same window and haven't grown out much at all, like King Reef. There's a few that sort of, grown out a little, And there's some that have started more recently and got to where they actually are. So the point I'm really trying to make is that a lot of reefs on the GBR, they were juveniles, youthful, doing all the good stuff that juveniles and youthful people do, things do 6,000 years ago, and effectively they've matured, and the vigour of reef growth in these areas has slowed down. Now when I say reef growth, I mean the accretion of the reef. The irony is in some of these reefs, you can see quite healthy coral communities growing on the fore reef slopes, but they don't seem to be actually building reefs at this point in time, and I don't understand why. So there's this sort of intrinsic marginality. As things get old, like me, I came here 20 years ago, I'm becoming intrinsically marginal. You just basically slow down and you're not as vigorous as maybe you were sometime in the past. So how is this useful? Well, one of the problems that we actually have is that a lot of the cores that we have come from reefs that have reef flats. And in fact, what I would argue is we need to start understanding more about some of these useful reefs and how they're growing. The problem is that they're technically difficult to actually get at, but that's going to be my next research project, effectively. And maybe they're not all the ones that we need to know about. Maybe we don't really need to know about these reefs that have done their dash. We want to know about the ones that are beginning their dash or halfway through it. So I think we need to increase the data set to try and capture some of these reefs that we haven't really got a good history about at the moment. But we do have a history, we do have enough information to know where some of these different sorts of reefs actually are. And without going into all the gory details, we can sort of predict and explain where we would find different types of reefs based on those 5 criteria that I mentioned before: the depth, size of the substrate, basically the relative sea level history, and a couple of other things as well. So I don't really want to go into that, but what I would say is that there are things that still I don't understand. But I'm not going to tell you I know all the answers, because that's a lie. But this is Pippon again. And one of the interesting things at Pippon is that we've got this reef, which I was showing you, grew to sea level and has basically gone from being a juvenile reef to a senile reef in about 1,500 years. And yet only about 1.5 kilometres away, there's a shoal. The top of it's about 8 metres below the surface. And it's growing it's the same size, it's growing effectively in the same location, and why isn't it also at sea level? Has it did it start growing later? Did it start growing and get knocked over? What are the controls on that? Because there is actually a lot of substrate where you would expect reefs to be. Down the Cat Bunks it's the same. They're big carbonate platforms which for some reason there is no reef on them. Why? I have no idea. If you were to say, produce me optimal habitat for reefs to grow on, that's it, but there's no reef on it. So understanding why reefs are in a place is one thing, understanding why they're not in some other places is also something that I think we need to actually look at, and I think that's a place where the geomorphologists can provide some of the information and the ecologists can provide their expertise, and that's something that I think really needs to be there. And just a plug for Rob Beeman. If you haven't had a look at Rob Beeman's outputs, he's produced these fantastic maps. And this is only part of it. You can blow this up in detail and you can see, very high resolution substrate. So we can actually look for the sorts of substrates on Rob's map that we would expect the reefs to actually start to grow on. And one of the things that's interesting is when you go to the northern GBR, which hasn't got any of, has got much reduced anthropogenic pressure, once again, there's large areas where you would expect there to be mid-shelf reefs and shoals near the surface because it's shallow, but they're not there, even though the substrate's there for them. So why not? And again, that's something that I think is worth looking at. So, I guess really what I'm trying to drive home here is that geomorphological timescales, even though they might seem long to ecologists, are often looked or perceived as geological, but they are actually relevant. These things do change through time at a rate that's pretty, in my view, quick. And I think if we don't take that into account, then we're potentially going to not have an optimal conservation plan. And the spatial scales are also important. All right, finally, just to finish off with something a little different, another sort of contribution of geomorphology to the management of the GBR is happening at Rain Island. So I think most of you would know that Rain Island is located up near the top of Cape York, and it's right out on the outer barrier. In fact, it's beyond the outer barrier. And it's a sand cave on a reef platform. And like all sand caves, it's basically composed of sand-sized sediments, which are the bits and bobs of the skeletons of the organisms that live on that reef. It's home to the largest nesting population of green turtles in the world, and I think most of you would know that a lot of turtles migrate there to nest every year. And there's a picture of a lot of turtles nesting on the beach. But in the last 30 years, research has shown that nesting success is only about 20% of what it should be. Well, it's only 20% of the total number of nesting turtles. Other comparable habitats, 60 to 100%. The hatchling success of the turtles that lay is less than 10%. Once again, comparable nesting habitats have a success rate of about 75. So things aren't going very well for Rain Island. And on top of that, the mortality rate of turtles because of getting caught on the beach rock or falling over the phosphate cliff is quite high. Up to 2,000 breeding females can perish in a high season. So these things combine to mean that if nothing is done up there, basically we could see the northern GBR population of green turtles dramatically decline over the next few decades. Now, even though the problem is for the turtles, it's clear, the biologists have been going up there and counting the turtles for several decades now, but it's clear that the root cause, at least of the major problem, is actually geomorphological. So one of the key things that happens is that the turtles are actually laying their eggs, and when the tide comes up, so a lot of the nesting happens in this backburn area. When the high tides come up, it floods the nest, okay? And the eggs basically suffocate or drown. The other thing, the only high area is this burn, because that's where the waves can bring the sand up to. And there's great competition and crowding on that burn area. Why is it low at the back? Well, basically the island is just built out over time, and only waves can bring new sand in, and that's why the high area is around the edge, whereas wind and just diminution of the sand sediments by the turtles themselves means that there's deflation and a lot of the stuff behind. So once again, this is all natural, but this is a high conservation area. This is a really endangered population, and I guess we just have to do something about it. The future isn't just uncertain for the turtles, however. So as I said before, the island, the cay, is made up of sand, which is all biogenic. It's all produced by reefal organisms. And you can form two types of sediment. Primary sediment, which is where the sand is actually formed at sand size, and then you can also have bioerosional secondary sediment, where you have bigger corals that break down into sand, and then that sand gets delivered. So there's a time lag in the second one, whereas the first one, when the organisms die, they're effectively available to be transported to the island. Okay, so we can have a look at the sort of suite of organisms and see what the major producers, what the major calcifiers are, because when I look at an island, I look at it as a sand pile, and I address it as a carbonate budget exercise. I know it has an ecological function, which I'm also very aware of, and I think the way to tackle this problem is to think of it as a carbonate budget problem. When you look at the sand on Rain, that's a handful of it, and what you'll notice is there's a lot of these orange things. And what those orange things actually are is that they're forams. Okay, they're a particular foram known as Bacillogipsina spherulata. So the island sediments are dominated by that foram. This is what they look like when they're living. They mainly live on epilithic algae out on the algal rim around the perimeter of the reef. But as they get transported, the little arms, the star sand arms, get worn away and fall off. So if they get transported quickly, so something is alive, then it dies, then it gets transported quickly to the island, it should have all its arms. Okay? If it's not got them, it's been either on the beach and the beach has been moving around, or it's been worn off in transit from the production zone to the island. And when we look at the sediments on Rain, basically what you can see is that about 50% of them are those forams. So there's a lot of eggs in the Bacillogipsina basket in terms of providing the sand for the sediment budget for that island. And one of the key problems is that if you turn that habitat off, or you do something to reduce the productivity of those organisms, then you have a pretty quick effect on the sediment budget. So where these organisms are basically living is on this this algal pavement. So this is just infrared, and obviously where the red is where there's vegetation. That's where the forearms are. They're also photosymbiotic, so they bleach, and they have pretty fragile skeletons. They're vulnerable to ocean acidification. So you can actually also reduce your sediment budget if you reduce the durability of the skeleton, which is also a major problem. Now, we did a fair bit of dating out there to have a look at the age of these sediments. And in a nutshell, the main thing you really need to know is that across the reef flat, basically nearly 4/5 of the sediment, or more than 4/5, are very, very young, less than 45 years old. The median age is only 11 years. So there's a really tight coupling between the biological productivity of the forearms on the reef edge and the sediment budget of that island, on which the turtles depend. That's really what I'm trying to stress to you here. So there's a lot of information there you don't really need to worry about. The key thing is that when we did this dating, we dated forearms with different taphonomic conditions. So these numbers aren't sort of thousands of years ago. That's if you pick up forearms that have got all their arms, some of their arms, or none of their arms, different taphonomic state, this is the sort of age band that we get for those two different corals. And what you see is across the reef flat, it's all pretty young. So once again, there's a real tight coupling between the forearm production and the delivery to the island. There's a lot of sand that gets lost off the island, so you have to keep replenishing it. Otherwise you go into negative budget. Okay, now we've done a fair bit of modelling on this. I didn't want to tell you about it today. My PhD student John Dawson's been doing a lot of it. And what it actually shows though is that if we don't do anything about our greenhouse gas emissions, by about 2060 we basically go into big decline. And so the island will be in effectively a hard to turn around negative sediment budget state from that point forward. If we go for one of the more kind scenarios, so RCP 4.5 or one of those ones, then we can actually push that out to about 100 years and the slope of the decline is much less, which allows us to maybe turn something around. So the point really that I'm trying to make here is that to understand what the long-term future for the turtles is at Rain Island, you really need to understand a bit about the geomorphology of the island. And the sediment budget of the island is key in that. And the sensitivity of those budget elements to future changes. Just to say though, as I stressed before, that this is a key site, and the feeling at EPA and Gurumpa is that we can't wait around for things to take their course. We have to do something now. So this is just a little diagram that shows the problem. So current nesting, basically the water comes up, they get drowned. So the adaptive management plan is to actually lift that area behind the burn. And there was talk about bringing sand in from various sources, but one of the things that I've been involved with over the last couple of years is trying to work out whether or not we could actually just get the sand from the island itself. So you might be able to make out these sort of lineations here. They were for a long time thought to be a thing called brine rock, which was problematic, but actually through a whole lot of drilling and augering and digging big holes, we worked out it's just beach rock. And this coast is built out this way over time. Okay? The volume of the island hasn't changed in 40 years. So the volume of sand, we've done detailed volumetric models, it's still the same. It's just where the sand is distributed has changed, which is why this is low. So what we've actually done is we've worked it out, and based on where we know the sand goes from season to season, there's a trial area down here, and just a few weeks ago, in fact, they had excavators up on Rain Island that have actually pulled sand back from the beach and filled that area up behind the berm over 150 metres to elevate the nesting habitat. And they've got a whole sort of experimental design going there to test. There's a few other things, there's pathogens and the like that may be problematic, but this is a test of whether or not this will actually work. And we did it at that time using geomorphological knowledge because we knew that there was going to be no impact on the substrate rocks, the hard rocks, the beach rock, etc. And we also knew that the sand would be moving back to fill up the area which the excavator would pull from over the next few months. And in fact, it's going to go in a couple of weeks, and it's by all accounts, pretty much you can't see where the excavators pull that sand, which is a much better option than bringing sand from somewhere else, which has a whole lot of biosecurity issues associated with it. So basically, that's hopefully a good news story, but without looking after the sediment budget in the longer term, I don't really, it's a bit of a band-aid. So thanks for listening to me sort of, preaching from the front here. I guess really what I'd like to say is that, geomorphological histories can provide valuable context for interpreting the current ecological condition. Geomorphological time and spatial scales, I think, are more applicable to ecological research and conservation planning than are broadly recognised, and I guess I'm on a little quest to try and maybe change that a bit. And carbonate budgets, I think, are really useful tools for understanding ecological and geomorphological links and ecosystem trajectories into the future. And if we come back to the stuff that was on Coral list, I guess what I would say is that, hopefully I'm right, that geomorphologists can and do make contributions to important, reef questions. So that'll do me. Anyone got any questions?
Scott, great stuff. If you take your Rain Island example and apply it more to submerged reefs, so the first part of your talk suggests that submerged reefs have an enormous capacity to cope with, say, sea level rise, because there's this sort of inherent ability for rapid change. But then if you think about the potential problems with acidification and warming, leave aside runoff or whatever turbidity, maybe that's not going to be there in the future. So what's your thoughts on that in terms of submerged reefs, not sort of islands?
Well, I think you're right. I think, there's been a fair bit of banter in science. There's a paper recently as well, which, somebody made a statement about, the reefs can keep pace as long as they're healthy. And if they're healthy, that's the issue. Because I think, we know that, we've got skeletons that are less dense. We've got a whole lot of issues which are really to do with calcification and basically the long-term integrity of the material that's being produced. And so I think there's no real easy answer. I think the rates that we see that are high in inshore reefs are because of the actual sediment. So what happens is that the sediment buries it and then bioerosion is limited. So as the reef grows up, it's always just keeping its head above the sediment, and the material that was produced, a decade ago is below where bioeroders pull it apart. When you go on the outer reef, that doesn't happen, and I think, in some senses, even though the water quality conditions are better, when they're under stress, they're probably under a little, they're handicapped even more than some of the inner reefs in terms of building structure. How good that structure is for habitat and a whole range of other, ecological or ecosystem functions, I guess that's something that, I'm not qualified to say, but I think it's definitely something that is worthy of investigation, probably hasn't been looked at. Does that answer your question?
Do you know why there's a gap in the first stuff that you shared on the inshore reefs?
I knew someone asked me. The answer is that I don't. But it's interesting, there's been a lot of work now from Japan, from the Eastern Pacific, and regionally through the Western Pacific, where it seems to see the same gap. Now, initially I would have said maybe it's to do with sea level falling, and on the GBR I might have thought it was to do with the outer GBR reaching sea level and changing the inner, mid-shelf, water quality. But I really don't know, and that's another thing. I should say, 3,000 reefs that are mapped on the GBR, and there's only about 60 reefs that have actually been cored. So there's more cores from a lot of reefs, but we have a pretty limited sample. And all the submerged reefs, so Tom Bridge, there's obviously, and those guys have found recently that there's 50% more reef that's submerged than the reefs that are being mapped, so in terms of coral habitat. So there's a lot of stuff that we don't know, and how that plays into this is unknown.
It's got the accretion rate stuff you were alluding to before. I was thinking of all the cross-shell differences we find on the GBR. But if you actually look offshore, for example, potentially the supply of food is really different. The species can be really different. The way vegetation is really different. There's a whole lot of factors potentially involved in those different accretion rates. Can you comment on? I mean, you've alluded to the like in the sediment sort of scenario, but I would thought offshore potentially growth would be much higher. Upland there, you've got.
Yeah, well, if you go in the mid-ocean, you go to mid-ocean atolls, you find rapid rates of reef accretion. There's no, most atolls have got big broad reef flats that are at sea level, and so you're right. On the GBR, I think some of the accretion rate is to do with basically export of the sediment. So when you're in those environments where you've got higher energy, episodically you basically coppice the whole lot and shift it off. And so, if you're looking at a core, effectively what you're looking at is the integrated accumulation without being able to work out what the export might be, which might be completely off the platform. So a good example of that, even for the inshore reefs, is a few years ago, Jez Roth and John Pandolfi's group, they had some stuff from Pelorus where they saw that they did really high resolution dating, and they said, well, the top 200 years is basically missing, so there's been an acropora collapse. But if you work on many of the inner reef islands, you get in, put your boat on the beach, and the first thing you do is you walk up over a big shingle ridge. So some of that reefal production, I'm not saying there hasn't been a collapse, but you have to remember that not everything stays in situ where you're looking at it. So the reef growth at that site is not the total cumulative amount of calcium carbonate production at that site over time. It's what's left there after a whole lot of other processes. And some of those material is actually being deposited onshore or off reef.
Just wondering, with the sediment that you saw laid down, and you said across cores on a reef you'd see a pattern where it's all been laid down. Do you get any patterns across reefs, like between reefs, where you've seen a sediment deposition in a general area? Or
look, the answer I'm going to give you is possibly. The problem that we have is that, as I say, we're dealing with transects, and then we're dealing with cores that are basically 9 centimetres in diameter. So, because the architecture of the reef, it's not like a book that every page is nice and flat and lines up. You know what it's like when it's a complex topographic structure, and so you can be same age where I'm standing to something here, and you can have a little basin, if you like, that's between a couple of bommies and whether or not you get enhanced accumulation in those areas. But we get those layers in enough cores to suggest that they happen, fairly broadly across, not necessarily the one reef at the one time, because even if that gets deposited, it might get washed away from where it's been deposited before the reef starts to grow over it. But there's sort of age bracketing as well, which seems to suggest that there's a bit of a system happening. I guess what I'm trying to say here is I'm not willing to commit that every now and then the whole reefs get draped in mud, because we just don't have enough cores and enough data to say that. But there's definitely periods of time when there's lots of mud, and only mud, being deposited in those systems, which is interesting because if you had cyclones, typically what you have is you have mud with then detrital material roll in with it. When you've got sort of river floods or whatever that might bring in a lot of mud, then it will just settle down over the whole lot, and you get a big thick layer of like buttery mud that doesn't have any detrital coral that's also been washed in at the same time.
I think he's selling some of the ecologists a little bit short.
Yeah, I know I am actually, but I thought
hear me out. Yeah. One of the things that people are very fond of is that fishing has an immutable global footprint. It trumps everything else in terms of looking at demography and abundance of fish. If you go out to the Central Pacific and look at reef systems and look at targeted fish, their abundance and demography, and if you do an analysis which takes into account not only fishing but spatial scale and the geomorphology of the reef, what I call reef configuration and structure trumps everything else. Fishing emerges at a much lower point in the scale, and moreover, some of the features which we think relate to the fish abundance, demography, are things which are probably changing at a scale which is relevant to the generation time of the fish, because some of them are quite long-lived, and you're talking about changes of only 15, 20 generations which are occurring
Yeah.
and having huge effects on the abundance of the fish.
Well, that's exactly what I'm talking about. And I will admit that when I wrote that abstract, I thought it was
I just thought
but I do think that there are. I do think that people could appreciate it more. And I know what you're saying is true, and I've seen it myself.
Right, I think we might wrap up there. Again, Scott.
All right.